now let's take a look at the idea of integrals involving secants and tangents. Now, the technique we looked at with sines and cosines, we're going to use the exact same idea. It's just simply different trig identities. If the power of secant is even and positive, save a factor of secant squared and convert the remaining factors to tangents. See, when the factor of sine was odd, we pulled one out, converted the cosine, because the derivative of cosine is negative sine, so we just work with that negative. When cosine was odd, we pulled out one cosine, converted it into sine, because the derivative of sine is cosine. Here, when secant is even, I'm going to pull out the secant squared. Because remaining secants, because it's in the even power, I can convert to tangents. Well, what's the derivative of tangent? Secant squared. So it's the exact same idea, just simply different trig identities. So this is an explanation of what we're actually doing in a generic form. And go ahead and take a look at that. But I'm going to jump in right away with an example. Now, I have the integral of secant to the fourth x times tangent squared x. So I'm going to write this as the integral of secant squared x times secant squared x tangent x dx. So I pulled out my secant squared. This will be equal to, see, I can rewrite the secant squared in terms of tangent, and secant squared is actually equal to 1 plus tangent squared. So I'm going to write this as 1 plus tangent squared of x. There's my secant squared times tangent, oh, I lost my squared there, times tangent squared of x. And then I have this last secant squared of x. Now, if I let u equal tangent of x, then du equals secant squared x dx, which is exactly what I have right here. So now I'm going to end up with this integral of 1 plus u squared times u squared du, which is simply the integral of u squared plus u to the fourth du. And so you see now this is in a nice polynomial form involving u's, which I can easily find the antiderivative of. So this would be u cubed over 3 plus u to the fifth over 5. But remember, u is tangent, so this will give me tangent cubed of x over 3 plus tangent to the fifth of x over 5 plus my constant of integration. So there's the solution to the original problem. Let's take a look at another example. Here, what if tangent is odd and positive? In that case, I want to save a combination of secant tangent. And then factor out the remaining and expand and integrate. Now, think about that. What this means is when I keep a secant tangent combination, and then I take that tangent squared and convert it into secants, well, if I let u equal secant, what's du? Well, the derivative of secant is secant tangent. So that's why I need that secant tangent combination that I'm going to save. So here what I'm going to do is I'm going to rewrite this as the integral of secant cubed of x. No, I'm sorry. Yeah, that's what I'm going to do. Tangent squared of x times, I have a secant x left and a tangent of x dx. Well, tangent squared I can write in terms of secants. So this is going to be the integral of secant cubed x times secant squared of x minus 1, that's my tangent squared, times secant x tangent x dx. Now, if I let u equal secant x, then du equals secant x tangent x dx, which is exactly what I have right here. So when I do that, I end up with this integral that looks like u cubed times u squared minus 1 du. So once again, I have this nice polynomial that is nothing but a polynomial in u. So I'm going to go ahead and expand this a bit and get u to the 5th minus u cubed du. Now I can easily find the antiderivative. So I will have u to the 6th over 6 minus u to the 4th over 4. But remember, u was secant of x. So this is actually going to be, or it gives us, secant to the 6th of x over 6 minus secant to the 4th of x over 4 plus my constant of integration. That's the solution to my original problem. Okay, see what's next here. If there are no secant factors, and the power of tangent is even, so I have an even power of tangent and positive, I want to convert a tangent squared into a secant squared, and then factor and expand and repeat as I need to. In other words, all I have is tangents. I didn't have the necessary secants. I'm going to make some secants and see what happens. Okay, so tangent to the 4th of x. I am going to write this as the integral of tangent squared x times tangent squared x dx. Now I'm going to write this tangent squared in terms of secant squared, which will give me the integral of secant squared x minus 1 times tangent x squared dx. Okay, that looks good. Now what I'm going to do is I'm going to go ahead and distribute that tangent, and this is going to be equal to the integral of secant squared x tangent squared x minus tangent squared x dx. Okay, what good did that do me? Well, what I'm going to end up doing is I'm going to rewrite this as two different integrals. I'm going to take a look at secant squared x tangent squared x dx minus the integral of tangent squared x dx. Okay, so first off, let's just deal with this. What can we do with just that by itself? Well, if I'm going to rewrite this one piece here. The integral of, I'm going to write this as tangent squared x secant squared x dx. If I let u equal tangent x, then du equals secant squared x dx, which is exactly what I have right here. So I can easily integrate that. So I can think of this as simply the integral of u squared du, which is u cubed over 3, which will give me, because u is tangent, will give me tangent cubed of x over 3 plus, I'm going to call it c1, my first constant of integration. Now I need to deal with this last piece right here. And let's do that right down here. Now, to do that, what I'm going to do is I'm going to rewrite this integral as secant squared x, oops, that's supposed to be a squared, minus 1 dx, because that is tangent squared, right? Now, the reason that I did that is because I know that this antiderivative is going to be nothing more than tangent of x minus x plus, I'm going to call it c2, because the derivative of tangent is secant squared. So there I am, I'm set. Now I need to combine these, and when I do, I will get the solution to the integral of tangent to the 4th x dx will actually be equal to this first piece, tangent cubed x over 3. I'm going to ignore c1 for a second, plus the second piece, which is tangent of x minus x. And then I'm going to simply combine c1 and c2 to be my constant of integration. And here's my solution. All right, let's take a look at another example. All right, if the integral is of the form secant m to the x dx, where m is odd and positive, what I'm going to do is integration by parts. So I'm going to write this as the integral of secant squared x times secant x dx. That's supposed to be squared. Now, if I let u equal secant of x, then du equals secant x tangent x dx. That means that dv must be secant squared of x, which gives me v equals the integral of secant squared, which is this tangent x. So if I put these pieces together, I get the integral of secant cubed of x dx equals uv, which is secant x tangent x, minus the integral of v du, which is tangent x, and du is secant tangent dx. So this is secant x tangent x dx. I need to work with just this piece for a second, and as a reminder, I'm going to circle this negative. I'm not going to pull that negative down right now, but let's not forget that we need to put that in later, or else things could go like really bad. So I'm going to say that I have the integral of tangent squared secant x dx, which I'm going to rewrite as the integral of secant squared x minus 1 times secant x dx. Now I'm going to distribute this, which will give me the integral of secant cubed x dx. I'm going to break it up right away, minus the integral of secant of x dx. And I'm going to go ahead and move this negative back in now. So this will be a negative. This will actually be a positive. So what I have here is that the integral of secant cubed x dx is actually equal to, I need this first part, secant of x tangent of x. Now this part minus the integral of secant cubed x dx plus the integral of secant x, which is ln absolute value secant x plus tangent of x. Now you see, I'm right back to where I started with here, except once again it's opposite in sign. That means when I move it over to the left hand side, it won't cancel it out. So that actually gives me 2 times the integral of secant cubed x dx equals secant x tangent x plus ln absolute value of secant x plus tangent of x. So if I divide by 2 now, what I get as a solution is that the integral of secant cubed x dx is actually equal to secant of x tangent of x plus natural log of secant of x plus tangent of x, all divided by 2. And now I'm going to add my constant of integration. All right, let's take a look here at the last example. If nothing else works, try converting everything to the sines and cosines. And that's what I'm going to do with this example. This equals the integral secant, that's 1 over cosine, times 1 over tangent squared, that's cotangent squared. So I'll have a cosine squared of x over sine squared of x dx. My cosine will cancel. And this will give me the integral of, I'm going to write this as cosine of x over sine of x times 1 over sine x, which is equal to the integral of, see, cosine over sine, that's cotangent. 1 over sine is cosecant. And that is really nothing more than a negative cosecant of x plus c, my constant of integration. That's it. That one fell out pretty nicely.